go. All right. So by the end of today, you should be able to interpret, analyze, and draw both position time and velocity time graphs. All right. So, okay. So like I said, last chapter we talked about instances where the velocity was constant. Okay, and we looked at a bunch of different types of position time graphs. All right. So before I start drawing here, why this velocity graph got moved? Oh, I see. Oh no, undo. All right, whatever. So last chapter we looked at all kinds of position time and velocity time graphs. So when you look at a position time graph, you can tell a bunch of information. For example, just by looking at a position time graph, you can tell whether the object, what direction it's moving in, if it's moving forward or backward. Okay? So show me with your hands, you guys. What does the position time graph look like if you're moving forward, say? Good. Sloped uphill, right? And backwards, it's sloped downhill, right? So in a minute, I'm going to draw, all of these different objects. An object moving forward fast, forward slow. Backward fast, and backward slow, right? The ones that are moving forward are going to slope uphill. The ones that are moving backward are going to slope downhill. Okay? You can also tell how fast the object is moving. So suppose we've got two objects moving forward, but one of them is going slow and one of them is going fast. The one that's going slow, the graph will look like that, and the one that's going fast is the one that'll be steeper, right? Okay? So for position time graphs, steepness equates to fastness. Cool? Are there questions about that? All right, so let's draw this. So suppose I've got one object that is moving forward fast. I'm going to draw that in red. All right? Because it's moving forward, I know that my graph needs to slope uphill. And because it's fast, I know it needs to be steep. Cool? All right, so my graph might look something like this. All right, now notice I chose to start the graph down here at a negative position. The only reason I did that was so that I would have room to fit the whole graph onto my, onto the window, right? But there's absolutely no reason why I couldn't have, if I had wanted to, drawn that graph up here, and that would still represent the same thing, right? Okay? But, just so that it fits on the graph, I drew it down lower. Okay? The only difference would just be sort of what your starting position is. Follow? All right, now, we've got the second object that's moving forward, but it's going much more slowly. The fact that it's moving forward means that it's still going to slope which way? Uphill, but because it's going slow, it's going to be, what's the opposite of steep? Let's use the word gradual. Okay, I don't know if there is a technical opposite to the word steep, but yeah, we'll just say gradual. Okay, so gradual means not steep. So my graph for my object that's moving forward slow is still going to go uphill, just not going to be as steep. So it might look like that. Again, there's nothing magic about where I drew it. I could have drawn it, I could have drawn it up here, and that would have been fine too, right? Good? All right. Now, what if we're going backward? Well, going backward means that the graph is going to, instead of going uphill, it's going to go downhill, right? But then we've got the same steepness relation, right? So this one here is going backward slow. So backward means it's going to slope downhill. And the fact that it's going slow means it's going to be gradual. So maybe that looks like, I don't know, this.
Why are there two green ones?
So why are there two green ones was the question, if you didn't hear it. Both of these green lines are going forward slowly. The only difference is the top one has a sort of a higher starting position.
Okay.
All right. So I drew them both because I want you guys to understand that there's nothing magic about sort of where you start the graph. Where you start the graph is just sort of describing what the initial position is, right? But the speed and the direction are determined by that slope.
Okay.
Good? Is everybody good with that? That's a really important concept. You guys good? Get your markers sorted out?
You gotta push really gentle with this marker.
I gotcha. Yeah. You don't want to ruin the tip on a good marker. No. All right. Everybody good? Okay. Finally, if we're going backward fast, so I'll do this one in black. So the fact that it's going backward means that I want to go downhill. And the fact that it's fast means I want to draw it steep. So something like that, right? So the drawing here is a little bit cluttered, but if you understand sort of what I wrote down here, you know, next to each of the phrases, I think that's the important part. All right. Now, I skipped one. If you're stopped, remember you guys, this is a position time graph. If you're stopped, what's your position going to do?
Zero.
Not necessarily zero. It's going to be constant. Okay, now a lot of you said straight. These are all straight.
Horizontal.
So horizontal. If you are stopped, you're going to get a horizontal line. All right, so let's do this one in, I don't know, purple. All right, so if you're stopped, you're going to have a horizontal line. Now, where you're stopped just depends, right? If you're stopped at a position of 3, then it's going to be up here. If you're stopped at a position of -2, it'll be down here, whatever. So I'm just going to arbitrarily draw in a horizontal line. There we go, that's stopped. And again, it could be anywhere. You could move this all up or down as much as you want. All right, any problems there? All right, now the big thing that I want you guys to notice is that in all of these, my velocity was constant, and therefore my position time graph is straight. And when I say straight, I just mean not curved. Cool? Okay, now, it seems a little silly. We just talked about constant velocity and made position time graphs. Well, let's look at our velocity time graphs, right? So, let's do stopped. All right, if you're stopped, what's your velocity? 0, right? And constantly 0. So what would my velocity time graph look like for this thing that's stopped? Not straight, but a horizontal line at v equals 0. So all I'm going to do is I'm going to grab my purple again. Pen, purple, right? Velocity of 0 is right here, right? So I want my velocity to be constantly 0. There we go. That guy is stopped. Okay? All right, now, all of these have constant velocities, don't they? So that means they're all going to be horizontal lines, right? So let's go back to the first one. Let's go to the red graph, the forward fast graph. All right, if you're moving forward at a constant velocity, so I guess here's what we need to do. We got to establish two things. So first of all, forward versus backward. How's the velocity different if object A is going forward and object B is going backward? What do you got, Steph? Sorry. No? I saw you make the right gesture. Sure? Spencer?
B would be negative velocity, negative positive.
Okay, good. It's not necessarily about which way it slopes, Cinderella. It's more about whether the velocity is positive or negative, right? Moving forward is positive velocity. Moving backward is negative velocity. Okay, is that what, I thought I saw you doing this, Cinderella. Was that?
Like this versus this.
I gotcha. So, sort of. So, moving forward has to be positive velocity. So these are both going to be positive velocity because they're both moving forward, right? So now we got to find a way to distinguish between fast and slow. So here's the easiest way to do it. What's the slowest you can possibly move? 0, right? So the closer your velocity is to 0, the slower you're going, right? So let's do the red one and the green one. The green one is going forward slow. So I'm going to draw forward because it's positive and slow because it's almost 0. And then the red one is going forward fast. So I want to have a positive velocity, but I want a big positive velocity. Those are both supposed to be horizontal. Sorry, those are both supposed to be horizontal lines, you guys, because they're supposed to be constant, right? So this is a constant velocity of 1 point something, and this is a constant velocity of about 5, right? So this is going forward at like 1 point something meters a second. This is going forward at 5 point something meters a second, but constant. backward slow or we can go backward fast. So backward slow is blue. So backward means it needs to be a negative velocity, right? And then slow means it needs to be almost zero. Okay, so there's backward slow. And then backward fast is going to live way down here. It's going to be a big negative velocity, right? So backward fast. Does that make sense, you guys, or no? Any problems? So you really need to make sure you understand this stuff before we move on to the next chunk. If you're struggling here, you're going to struggle later. So, all right. Who can tell me why all of my velocity graphs are horizontal? Because the velocity is constant. Good. Everybody cool with that? All right. And how is that represented on my position time graphs? How's constant velocity represented there?
Straight line.
Because they're straight, not curved. Good? All right. Finally, does everybody understand that the green line on my position time graph is the same as the green line on my velocity time graph? They're both describing the same motion, just different ways, right? This is saying my position's increasing at a constant rate. This is saying my velocity is positive and constant. That's the same thing, right? Cool? Any questions before we go on? All right, so this theoretically is stuff that we learned in the last chapter. We really didn't talk about these velocity graphs because there wasn't much to talk about, right? They're just horizontal lines. Are we good? All right, so this chapter we're talking about changing velocity. We're talking about acceleration. All right, so your acceleration your velocity can increase, positive acceleration, or your velocity can decrease, negative acceleration. And that's going to result in these position time graphs. What do the position time graphs look like if you accelerate, you guys? They're curved, right? Instead of being straight lines, right? Does that make sense? Okay. So which way they slope depends on which way it's going, but they're going to be curved if you're accelerating. Okay? So this first example is sort of designed to help you understand why the position time graph curves the way that it does. All right? So this example is sort of a one-time deal just to help you see where that curve comes from. All right? So it says, what if we spend 2 seconds not moving, and then I added something. This is not in your version of the notes, so write this down. What if we spend 2 seconds not moving at a position of negative 5 meters? All right? For future reference, if I don't give you a starting position, let's just assume it's 0. Okay? A lot of times I forget or just decide that it's not important, and I won't give you a starting position. So just assume it's 0. But here, I want to give you one so that everything will kind of fit nicely onto our graphs that I gave you here. All right? Everybody good? Okay, so we're going to spend 2 seconds not moving, and then we're going to spend 2 seconds going 0.5 meters a second, and then 2 seconds going 1 meter a second, 2 seconds going 1.5, and then 2 seconds going 2 meters a second. Everybody good up there? Don, you doing okay? Everybody good? All right, so let's do this. Now, what I'm going to actually do, you guys, I'm actually going to do the velocity time graph first. All right, and that's going to be, as we're moving forward, that's usually what we're going to do. We'll do the velocity time graph first, largely because it's easiest. Okay? So, let's do this. I'm going to color code. So, 2 seconds not moving, we'll do that in blue. So, here's my velocity time graph. How much time do I need? Let's see, I've got 2 seconds not moving. So 2, 4, 6, 8. I need a total of 10 seconds. And if you look at the graph, I think there's 10 seconds here. So let's just number this. My time is going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then my velocity needs to include everything between 0 and 2. And I'm sorry, I didn't give you much room to write in your velocity, so to do the best you can. So we'll make the middle be 0, obviously. And then we'll skip, and we'll go 1, and then 2, like that. Make sense? Okay, so 2 seconds not moving. What's my velocity while I'm not moving, you guys? 0. I only drew that really hard so you could see the blue over the axis there. right? So that's v equals 0, right? Notice it's at 0, right? Cool? All right, then I'm going to spend 2 seconds going 0.5 meters per second. Well, here's 0.5, and I want to spend 2 seconds doing that. Right? Questions or no? About why I drew that like that? This is just showing that for the next 2 seconds, my velocity is 0.5, right? And then for the next 2 seconds, we're at 1. And then for the next 2 seconds, I'm going to recycle blue just because I ran out of colors. We're going to go up to 1.5. And then for the last 2 seconds, the velocity is 2. Now, those should just be nice, straight, horizontal lines. I kind of scribbled them in just so that you could see them from wherever you're sitting. But good or no? All right. Now, if in math classes, have you guys learned about piecewise functions? So that's what this is. It's sort of a sloppy piecewise function. Really, I should have a solid dot and an open dot at one end of each of these. We're not going to worry about that because this is the only time we're going to get a graph that looks like this. So as long as you understand that the velocity is constant, and then it's constant, and then constant, 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 you're good. Everybody happy? All right. Now let's do our position time graph. Okay? So let's see, our position starts at -5. So you wouldn't know this unless you'd done the calculations, but it turns out that if you just make each box be 1 meter, everything works out very nicely. So we're just going to go -1, -2, -3, -4, -5, and then 0, 1, 2, 3, 4, 5. Cool? All right, so let's see. We're going to spend 2 seconds not moving at a position of -5. So should my position time graph just stay at 0 because I'm not moving? No, because my position isn't 0. What is it? -5. So my position should stay at -5 for 2 seconds. Excuse me. Does that make sense? That's what this is telling me. My position that I start at is -5 meters. Cool? Now, if my starting position had been 0, then it would live up there at 0. Okay, that would just move the whole graph up to, starting at 0. Otherwise, everything would be the same. Okay. All right, then I'm going to spend 2 seconds going 0.5 meter per second. So check it out. All I'm going to do is I'm going to go, remember, my time axis. Oh, I forgot to number my times. 1, 2, 3, 4, 10. There we go. All right. So I'm going to move. I guess it didn't really say the direction. I guess you can assume it because they're positive that we're moving forward. So my position is going to increase by 0.5 meters for 2 seconds, right? So I'm going to go over 1, up 0.5 meter. Over 1, up 0.5 meter. So in those 2 seconds, I went 1 meter. So now my position is -4 at the end of those 2 seconds, right? Everybody good? Problems? All right. In the next 2 seconds, I'm going 1 meter per second. So in 1 second, I'm going to go 1 meter. In 1 second, I'm going to go 1 meter. Connect the dots. What do you notice? What happened? From blue to red to green, what's the graph doing? It's getting steeper, right? And you can kind of begin to see, oh, it's sort of like curving, right? It's not exactly curved, because there's these sort of straight chunks, but you can see sort of what's happening, right? All right, so for the next 2 seconds, I'm going to go 1.5 meters. So I'm going to go 1 second, 1.5 meters. 1 second, 1.5 meters. And connect the dots. Oh, that's a fail. 1.5 meters, 1.5 meters. There we go. And then for the last 2 seconds, I'm going to go 2 meters. So 1 second, 2 meters. 1 second, 2 meters. Cool? So notice the position time graph gets steeper Why? In simpler words. Yeah, you're accelerating. In simple words, what are you doing? Speeding up. Remember, the steeper you're going, the faster your position time graph is. Cool? Any problems? All right. I think we're good. If you guys are good. Are you guys good? All right, so here's the issue. The next slide says this, so I'll skip ahead a slide in a minute, but I still see some of you writing. In real life, if you were to do this, if you were to speed up from 0 to 2 meters a second, it wouldn't work this way, would it? Like, you wouldn't just go 0, and then go 0.5 meters a second, and then go 1 meter a second, right? Like, your speedometer would start at 0, and then it would gradually increase until you get to 2, right? But you would literally hit every speed between 0 and 2, wouldn't you? Instead of just hitting these sort of 5 individual speeds, right? Okay, so what we need to do is we need to replace this with the same thing but gradual. So all that's going to happen is my little stepped line here, my stepped graph for my velocity time graph is going to become a nice straight line. And this sort of chunked line is going to become a nice smooth curve. Follow? All right, any questions before I go on? Awesome. Bam, here we go. All right, so this says what I just said. All right, so an object moving forward from rest and speeding up. Well, our velocity started at 0, and then at the end of 10 seconds, the velocity was 2, right? So, oh, I don't know what just happened there. That was weird. Oh my gosh. Seriously? Why does technology hate me today? Oh, because I'm stupid. That's why. There we go. All right, so our velocity started at 0. Eventually it became 2. All right, so really, you guys, what I'm most worried about here is the shapes of the graphs. Okay? So what this represents is an object that is at rest, and then it moves forward because the velocity is positive, and it gets more positive, so it's speeding up, right? Cool? And my position time graph starts, it's got to slope uphill because we're moving forward, and it's got to get steeper because I'm speeding up. So, curved. All right, so let's make sure you guys understand each property of the graph. So how do I look at my position time graph and know that it's moving forward? Because it's a positive slope. It's sloped uphill, right? So my position time graph, I can look at this and go, oh, it's sloped uphill. That means it's moving forward, right? All right, how about on my velocity time graph? How can I look at the velocity time graph and know it's moving forward? Remember, what's the difference? In terms of velocity, what's the difference between moving forward and backward? Negative and positive, right? So the reason I know this is moving forward is not because it's sloped uphill. The reason I know it's moving forward is because these are positive velocities. So that's how I know that it's moving forward. My position time graph is uphill. My velocity is positive. So can you guys kind of see I'm making like a little table here? Good? All right, how do I know it's speeding up? Well, on my position time graph, I can tell it's speeding up because, what is it, X?
It's curving.
Okay, it's curving, but there's something specific about the way it's curving. Okay, so if you're not sure, look back, you guys. How did we decide? Oops, I went too far. How fast it was going was determined by the steepness, right? Steeper equals faster, right? Steeper equals faster. So check it out. At the beginning, it's not very steep, right? And then it gets steeper and steeper and steeper and steeper. Like imagine driving on this thing, right? It's getting way steeper, right? That means it's speeding up. because it's getting steeper. Cool? All right, and then look at the velocity time graph. How do I know it's speeding up? The numbers are increasing, yes, but you got to be careful because that won't always, they're positive numbers increasing, right? The way that I always say it is it's getting farther from zero. The velocity is getting farther from zero, so it's speeding up, right? Because the slowest you can go is zero. So velocity, exactly, and then, yeah, so then you get jacked up, right? So velocity is getting further or farther, ask an English teacher, I don't know, from zero. That is, for whatever reason, further, farther, you never got it. I'm good with your, and your, and there, and there, and it's and it's, but further and farther, no idea. I gave up. All right, are we good? Does this make sense?
Yes.
All right, so this is one of 4 possibilities. In this example, we're going forwards and speeding up. But you could certainly be going forwards and slowing down. So let's take a look at what that would look like. That was a bad sentence. All right, moving forward and slowing down. So we're moving forward. What should my position time graph look like?
Uphill.
Should go uphill, right? And it's slowing down. So it should get less steep, more gradual, however you want to think of that, right? So it's going to get less steep. You could also write more gradual. So I need a thing that goes uphill and gets less steep. Uphill and gets less steep. Right? At the beginning it's very steep, and then as it goes, it gets less steep. Make sense? Everybody good? Okay. Now, velocity. We're moving forward. That means that the velocity is positive, and we're slowing down, so it goes towards zero. Gets closer to zero. So I need a positive velocity that gets closer to zero. That's supposed to be a straight line. And it really should never go into the negatives either. Because once it goes negative, then your velocity is, then it's going backwards, right? Steven, you okay? You sure? All right.
Wait, so if we're slowing down, it gets closer to zero?
Yes. Oh. Tell me when I'm in your way, Adam. You've got that. Bad seat. All right. Any problems with what we've done thus far? Okay, next. So we've looked at moving forward. Now we've got to look at moving backward. So now we've got an object moving backwards, but speeding up. Okay? So, if you're moving backward, what's the position time graph got to look like if you're going backward? It's got to slope downhill, right? And speeding up means it needs to get, it's got to get steeper, right? So I need to go downhill and get steeper. All right, so I'm going to start at the top of the graph just to give myself room. But again, there's nothing magic about where you start. You know, I could start down here at a negative position if I wanted and just, you know. But here we go. We want to go downhill and get steeper as we go. So, right? Triple black diamond. Everybody good? All right. Now let's look at our velocity. Because we're going backward, our velocity is negative. So now it's got to live down here, and we're speeding up, so it yeah, what do you got, Steven?
Goes down away from the zero.
Goes away from 0. Gets further from 0. So it's going to do something like this. Again, that's supposed to be a straight line. You good, Will? Is this making sense?
Yep.
Yeah. Cool. Isla, how about you? You doing okay back there? Everybody happy? All right, now be careful. Up until now, I've been really focusing on this idea that when, and this will come back in a second, but when we talk about acceleration, I keep saying, make sure you use the word velocity. Make sure you use the word velocity. Here's why. In this example, is the object speeding up or slowing down? Speeding up, right? But look at the velocity. What's the velocity doing? Look at, don't think about it too much. Look, you walk into the room, you look at this, you go, oh, the velocity's decreasing, right? Look, it's going downhill. That means decreasing, right? So here's an example where your object is speeding up, but the velocity's decreasing. It's just getting more negative. It's going in a negative direction, faster and faster and faster. All right? Everybody good?
Yeah.
All right, last example. We got to do backwards and slowing down. So backward. What's it going to look like? Because we're going backward.
Down.
Position time graph will go downhill. And since we're slowing down, it's going to do what?
Less steep.
It's going to become more gradual, less steep. Again, I don't care which way you say it. Less steep. So I'm going to go downhill and get less steep. So that's going to look something like the first half of a half pipe. I am worried that I didn't make that curved enough. I really want to make sure you guys understand that that's curved. That's a little better. Cool? All right, now velocity. Since we're going backwards, our velocity should be negative. And then since we're slowing down, it gets closer to 0. So velocity is negative, gets closer to 0. Cool? All right. I want to go back and add one last thing to all of these. You'll have room to fit it in. It's going to be like 4 letters, okay? Or 4 symbols, I guess. We got to talk about acceleration. All right? So, first of all, if you haven't written this down yet, you need to write this down. You should have, hopefully, 3 sets of notes ago. Negative acceleration means velocity is decreasing. And positive acceleration means that your velocity is increasing. So let's go back for each of these and decide if the acceleration is positive or negative. So in this one,
Positive.
so this is the first one we did. The acceleration is positive. Why?
Velocity's increasing.
Look at the velocity. It's increasing, clearly, right? It's going uphill, so the velocity is increasing. So this is acceleration is positive, which means this one's also positive, right? And they're always going to be the same because they represent the same motion, right? So I don't know why I wrote it twice. In fact, let's just do this. Acceleration is positive because the velocity is increasing, right? Okay. How about this guy? What's the velocity doing? Increasing or decreasing? Decreasing. So that means the acceleration is negative. Acceleration, negative. Does that make sense? All right. Over here, what's the velocity doing? Decreasing. Even though we're speeding up, this is decreasing velocity. Look at that graph. That's totally decreasing. And therefore, my acceleration is Negative. Look, you guys, the velocity's decreasing. So the acceleration's negative. The velocity's getting more negative. That's a decrease. So the acceleration's negative. And finally, this last one we did, the acceleration is positive because the velocity is getting less negative. It's increasing. Cool? All right. We're only going to have time for one example with numbers today. So we're going to do one, and then I want you guys to try examples 2 and 3 tonight, and we'll go over them in class tomorrow. All right? Cool? All right. So any questions on what we just talked about here? All right, Mr. McGuire uses a different sort of way to remember these 4 separate graphs, and I'll try to share that with you tomorrow. Yeah, he gives them all names, and yeah, you know, whatever, different preferences. Okay, so, all right, so let's do one with numbers. All right, so we've got a problem here. Roy's, I don't mean a problem like, oh no, a problem. I mean a problem like there's a problem here that we need to solve. Right? Roy's sitting at a green light that turns green. He accelerates, reaching a velocity of da-da-da-da-da-da. What's the first thing I should do? Write down everything you know. Write down everything you know. All right? So Roy is sitting at a light which turns green. Ooh, hidden information.
0.
Something 0. Initial velocity is 0, right? He's sitting. And then the light turns green. So before the light turns green, his velocity is 0. All right. He accelerates, reaching a velocity of 24 meters a second. So is that my acceleration? Why can't that be acceleration?
It's not meters squared.
It would have to be meters per second squared. But yes, right idea. Meters per second squared. So that's not my acceleration. It's my final velocity at the end of 4 seconds, which is my time. All right. Then it says make a position time graph and a velocity time graph. Assume the traffic light is a position of -16. So -16 meters is my, what's that, my displacement?
Initial position.
Okay, very good. That's initial position. It's not telling you how far he went. It's describing a location. And it's saying when he began, his position was 18, right? Cool. Now, to graph this, we need to know every variable that's on the board up there. If you look at your list of equations on that toolbox that I gave you, you need to know all of the values. So the things that we don't know, in no particular order, are we don't know our acceleration, we don't know our displacement, and we don't know our final position. So we need to find each of those things using those equations. And that's what we just spent the last couple days working on, right? All right. So I'm not going to write out the math. I'm just going to write out the equation that I would use. So to find the acceleration, look at the board up there. What equation would I use?
VF squared minus VI squared.
No, because I don't know my displacement. You're talking about the vice grip there in green?
Yeah.
Yeah, VF minus VI over T, the ax, right? So here we go. VF minus VI over T. Do you guys agree that I can use that equation and find the acceleration? Cool. So do it. Plug in your numbers. You end up getting 6 meters a second squared. Cool? Now, to find the displacement, you can actually use any of those equations. You can use the screwdriver, the drill, or the vice grip. They'll all work because we know everything we need to know. Most people seem to prefer the screwdriver, so we'll go with that. And it ends up giving you 48 meters. Cool. And then to find your final position, there's only one equation that has position in it. So what are you looking at up there, you guys? To find the final position, there's only one equation up there. Nope, that's final velocity. We want final position. There's only one equation that has XF and XI in it. Yeah, what do you got, Steven? What do you got?
Tweezers.
The tweezers, right? Down at the bottom, written in blue and red. See them hiding down there at the bottom? If you had 3D glasses, it would jump out of the screen, out of the board at you. Right? So we can use this guy, displacement equals final position minus initial position, and solve. Or, if you understand what the numbers mean, you can just think about it. Check it out. I'm going to start at a position of -16, and then I'm going to go forward 48. -16 plus 48, it ends up giving you 32 meters. So you can either use the equation in algebra, or just understand what, what displacement and position are to each other. Cool? All right, so now that we've got all of this stuff, now we just graph it. All right, and I'm going to kind of plow through this because we only got a couple minutes here. I need 4 seconds to fit on my graph. I've got 10 boxes, so let's just go by every 2 is 1. So 1 second, 2 seconds, 3 seconds, 4 seconds. We don't need 5. Over here, I'll do the same thing. 1, 2, 3, 4. All right, tip number 1. This is huge. I want you guys to get in the habit of always making your velocity time graph first. It will make your life easier for reasons that will become apparent when we get into problems that are a little bit harder. All right, so check it out. What does the velocity do, you guys? It starts at 0. All right, and then after 4 seconds, it's 24. Oh, I got to number this. Let's see. So I've got 5 boxes. I got to fit in 24, so I should go by 5s. You could go by 6s, I guess, and get up to 30. That would be totally fine, too. So you know what? I'm going to go by 6s. I like that better, because that's what my acceleration is. So we'll go 0, 6, 12, 18, 24, and then 30. We just won't use the 30. Okay? So then, at the end of 4 seconds, my velocity is 24. And then connect the dots. And you should, really use a ruler. But cool? So this graph shows my velocity steadily increasing from 0 up to 24. Good? All right. Now, the position graph. Let's see, here's what I know. I know I've got 4 seconds, and my position has to go from negative 16 up to 32. So here's a position of 0. I got to get up to 32. I got 5 boxes. What should I number by? 8. Yeah, 7 would work, but it's a weird number. Let's number by 8s. And that actually works, too, because all of our numbers are multiples of 8 here, right? So let's see, our position's going to go 8, 16, 24, 32, 40, negative 8, negative 16. All right, so eyes up here for one more minute. Check it out. Our position starts at negative 16 and ends at 32, right? Can I just connect the dots with a straight line? No. Why? It's got to be a curve because the velocity is not constant. So I'm going to give you 2 choices. I want you to pick the right one. There are 2 ways I can draw a curved line from between those 2 red dots. I can use this blue one, or I can use the green one. Those are both curved, right? Which one do I want?
Blue.
Blue. Good. Why blue? What's the car doing that tells me it's got to be the blue one?
Speeding up.
Speeding up, right? The car is speeding up. That means the graph has to get steeper. Oh, shoot, I didn't draw that blue. Because speeding up. And that means that the green guy, not so much. Cool? All right.